Okay, so we'll start with a new topic, and I left off in the last lecture where I was trying to write down a proof for the construction of the epsilon 1 plus epsilon spanner. So I don't want to go through the proof in details. I just give you an idea and leave it as an exercise. It's rather simple actually. Just have to fill up the details. So before we start on this new topic, I just open up the page and tell you what needs to be done. Okay, so we are trying to prove this by induction, right? So these two, these 2 point sets. These are well separated point sets, right? These 2 sets are well separated. Okay. We are trying to prove by induction, induction on the pairwise distances. Okay, so we have a set of n points. Okay, set S of n points. The pairwise distances could be ordered, right, in terms of increasing distances. Let's say. So let's say the pairs are something like P1, P2, then P3, P4. So these are the distances in order of increasing distances. The n choose 2 distances in order of increasing distances. So we do the proof by induction on this sequence, right? So suppose we have proved that the spanner property, that is distance in the graph between points x and y is no more than 1 plus we are using a delta spanner, I think, yeah, delta spanner 1 plus delta times the Euclidean distance between x and y. Okay. Okay. So we need to prove this for every pair of points, and suppose we have done it in this sequence for some of these pairs. So suppose that now we are dealing with pairs of points P1, P2, and for all distances less than P1, P2, this holds. That's my induction hypothesis. Okay. Now what do we do? The construction was nothing but for each of these well separated pairs, we have a representative. We just pick an arbitrary representative. So suppose this set is did I name this set? Suppose let's call it capital U and capital V or something like that. So this is representative capital U, this is some representative capital V. Okay. This edge is what we add to this spanner, the spanner that we are constructing. Okay. This edge is explicitly added. Okay. And we claim that everything is taken care of by the sets of such edges. So, and the induction proof will use this fact. Now, since we are assuming that all distances less than P1, P2 is taken care of, because these are well separated sets, subsets, it means that the distances within the subset, okay, they are already taken care of. Okay. Because these are well separated pairs, so distances within the subsets are much less than the distance, or at least epsilon fraction less than this distance. So, everything within a subset is already taken care of. In particular, okay, this distance in the graph is already less than or equal to 1 plus epsilon times the Euclidean distance for this connection. Okay. And we can also argue that the distance between RE, the representatives of the 2 subsets, okay, is not more than some constant fraction times the distance between P1 and P2. That is the Euclidean distance, right, because it is well separated. Okay. The Euclidean distance between the representatives of these 2 sets are not very different from basically any of the pairs chosen from across the 2 subsets. Okay. So that is one property we are going to use. The other property we are going to use the induction hypothesis, that this distance in the graph is already captured in the spanner. Okay. And you just have to put the triangle inequality to figure to argue that in the graph, okay, this distance is not going to be more than 1 plus delta times the Euclidean distance. Okay. So that I just leave it as an exercise, and you can complete that. Okay. So with that, let's move over to the next topic. Okay. What are epsilon nets and what are VC dimension? I think you have seen, you have heard the first term before. Am I right? So at least I believe that when you're talking about these cutting partition trees and cuttings, did this term come up at all when Professor Agarwal was lecturing? Epsilon-Nets? Or you don't have recollection anyway. So this Epsilon-Nets is conceptually is no different from the definition of the 1 by r cutting used to construct the partition trees. Okay. So, but we will actually explore in depth about what these things are. So, these have very deep combinatorial consequences actually. Right. So, let me introduce with a problem and give you the motivation, what started off this, and then this has so this was first discovered in the context of what is called hypergraph theory. It was back in like early 70s or so, and VC denotes actually names of the two authors, two Russians mathematicians, Vapnik, Chevronenkis, I think. Chevronenkis. So VC dimension is short form of this. So they discovered some nice combinatorial properties, okay, for certain subset systems, okay, and which later, very soon found huge amount of applications in all kinds of fields, especially the people in learning theory make heavy use of this. Then even in geometric searching, people make lots of use of this, and essentially in any subset system that satisfied a certain kind of property, okay, which is basically this VC dimension. So, VC dimension is some property, okay, if a subset system satisfies, then you can find let us say, so I will just describe that problem, find covers of small size essentially. Okay. Okay, so let me introduce with a generic problem. So, so we have some population, okay, which are nothing but, let us say, vertices of the hypergraph, okay, and there are some groups of people, okay, and the groups of people are nothing but subsets of these the set of people of the population, okay. Okay, so let me mark this out. Okay, this could be one subset, this could be another subset, this could be another subset. The subset system and hypergraph, they are basically the same thing, right. So, there are all kinds of subsets, or you can say maybe interest groups of population, okay. Special interest groups maybe. Okay, with vested interests, okay. Okay, one very common problem is that we want to do some kind of survey on this population. Okay, we have a certain opinion poll maybe that we are trying to conduct, okay, like was the Commonwealth Games successful? Okay. Now, and different groups of people may have different opinions. Okay, so as I said, the vested groups may have different people. The people who organized it, they will certainly say that yes, it was successful. Okay, the people who participated, they may have a split opinion on that, and the people who bore the brunt of all this construction will certainly say nothing was successful. And now, for the investigating agencies got into it, and they have to start out with the assumption that everything was corrupt. Okay. So, but suppose there are an opinion poll. Okay. Now, in a democratic society, what happens is that we tend to go by how large the size of the group is, right? We don't really care what kind of vested interest that group has. Somehow democracy is supposed to take care of everything. No doubt that it was said that it's a system of government for the fools, by the fools, of the fools, right? That's Aristotle, right? Anyway, so we only go by the size of the group. Okay, the bigger the group, we believe that they have the right or the authority to be right. Okay. So these subsets basically represent those groups. Okay, And then what we want to make sure is that when we do an opinion poll, okay, we do not actually go and ask every person, right. If you could ask the entire population, of course, then we get a very accurate picture of, okay, so here is a group of people who think this way, here is another group of people who think that way, and blah, blah, blah. Right. So, that is not possible. All the opinion polls that are conducted by the media essentially on the basis of a sample. Right. Some subsets, a small subset that they can realistically actually go and spend a few minutes with and get their feedback. Okay. It can be with a phone call, could be a letter, could be, they stick a microphone up your nose, something like that. So, but then when the sample is selected, if the sample is not selected thoughtfully and properly, then of course, finally the opinion that comes out of it is could be completely fallacious. Okay. And that is what often happens when you see that opinion polls go wrong. Actually, the basic theory of opinion poll is quite sound, statistically it is very sound. The problem happens is either the sample has not been chosen properly, or that a large enough sample may not have been chosen, both ways. Okay. The sample needs to be chosen properly, maybe it should be a proper random sample. Okay. So, maybe it was not really random, or that not enough people were consulted, the sample size was inadequate. Okay. And if both these things are right, I mean there is some formula. So, if you satisfy these two criteria, that it is a large enough sample size and the sampling was done properly, then there is a mathematical formula that, let us say, the opinion poll is going to be correct with any almost probability tending to almost 1. Okay. So, there is a fairly sound theory on that. Now, here it is slightly different. What we we intend to do, as I said, is that the groups that are large, only the large groups matter, let us say, only the large groups matter. How large is large? Okay. So, let us choose a fraction, let us say larger than some epsilon times n. N is the size of the population. Right. So, some fraction epsilon, let us say epsilon is between 0 and 1. Right. So, maybe epsilon is 10%, 5%, 1%. So, we are saying that unless the group has at least 1% size of the population, really does not count. Right. And then what you do, you basically so then you want to sample in a way. Okay. So, we want to find or choose a subset such that, okay, number 1, we must have at least one representative from each of the large subset. Well, by large I mean that at least epsilon n size. Right? And of course, the objective is not just to have at least one representative. This subset that we choose, okay, we want to choose as small a subset as possible to satisfy this condition. Right? I want to choose as small a subset as possible and satisfy the condition that every large subset is represented. Right? So, this is a somewhat weaker condition than perhaps someone who is interested in the fact that, okay, just choosing one may not be adequate. Okay? We really want a representative of the a representative fraction of the subset. One possibility is this one, that I want at least one person to be picked in the subset of the sample. The other one may be more stringent, saying that, okay, I mean if there are two groups of people, okay, one is let us say about 20%, another is let us say 5%, then the subset that I pick up, okay, must capture the relative sizes. So, the subset that I pick up, the one that has largest subset should have more representatives or proportionately more representatives than this smaller subset, right. So, that is another condition that you may specify, that say so if M is the size of a subset, okay, and let us assume that again we are only talking about the large subsets, not arbitrary subset, arbitrarily small subsets. M is larger than epsilon n, okay, then the number of representatives R of M should be such that R of M is roughly about R of M over R. Okay, the fraction of sample chosen from that group divided by the actual size of the sample. Okay, so R is the size of the sample. Okay, so R set of size R is roughly, can you complete that? Right. So, whatever is the fraction that population that group represents of the entire population, my subset should kind of capture that. Okay. So, this is a more stringent condition, and probably it is a more fair condition in the context that I pose the problem. Okay. So, the question really here is that how small can R be to guarantee these things? Okay. How small to guarantee? Well, I mean there will be two different bounds presumably for condition 1 or condition 2. In fact, you can see that condition 1 is kind of a subset of the condition 2. If we can if we can satisfy condition 2, then condition 1 will be also satisfied. Okay. So, any ideas how do you go about this, and what does it look like, this problem that I pose right now? It should be something familiar actually, it's not such a new problem actually. So, what are we trying to do? We are trying to hit some of these subsets, right, by choosing, see what is it, look at this figure. Okay. We are trying to, let us say, color some of these points, which is basically I am picking them in the sample such that I hit all these subsets, right. So, it is a hitting set problem. It is a hitting set problem, right? Except that I am interested to hit only the large subsets. Okay. So, the other subsets do not even count. Okay. So, I can simply forget about those and pose it as a hitting set problem. So, if I pose it as a hitting set problem, then what is the obvious way of solving it? Yeah, greedy, great. So, if you use greedy, you can solve the problem. But let us say that I am not even looking at at any algorithm right now, I am only thinking in terms of the bound of R. But greedy gives a reasonable solution in terms of that, the bound also. So, if you assume that the greedy bound is something that we can achieve because it is a constructive solution, then would you remember what kind of bound you get? It is some logarithmic factor somewhere, right? Okay, all right. So, so since I am not again, I am talking about a bound. Let me do the following. I'll do a calculation, okay, a very elementary calculation. I'll say that choose, finally the bound will be very similar to the grid, okay. Choose a vertex. Now I am talking about that graph, the hypergraph, okay. Here is the vertex and the subsets are the hyper edges, right. So, choose a vertex with probability p equal to 1 by epsilon n to be in the sample. Okay. So, for every vertex, okay, okay, so there is not just this quantity, there is another quantity I am going to add on to it. Okay. So, I will actually multiply this by, so I will just use a, you will see why I am doing it in a different color. So, I am going to choose every vertex to be in the sample with probability 1 over epsilon n. Okay. This is the size of that large subset, okay, but with a slight twiddle factor with the extra log n. So, if I do that, so what is the probability that a large set, a large subset is not hit, that we do not pick any representative span. So, I am trying to answer question 1 here, not the second question. So, each vertex will be chosen with this probability. So, if something, a large set subset is not hit, okay, that probability is that none of these chosen vertices, okay, is going to hit it. So, that is 1 minus p, and they are being chosen independently, okay, with probability in sample. So, 1 minus p, the probability is not going to be hit, okay, and all these n vertices basically, sorry, this epsilon n vertices are not going to be chosen, right. So, look at that particular subset, the large subset, okay, each of those vertices are going to be picked independently with probability p, and because we have not picked any of them, it means that all those epsilon n vertices have not been picked, right. So, to the power epsilon n. Okay. So, which is, now if it is a larger subset, the probability will be even smaller than this. Okay. So, let me work with just the, the epsilon n subset. Okay. So, that is 1 minus 1 over epsilon n log n to the power epsilon n, okay, or so I can rewrite this as 1 minus 1 over epsilon n over log n to the power epsilon n over log n to the power log n. Why did I write it like this? Because this term is less than or equal to 1 over e, right. Okay. So, then this is basically 1 over, this whole thing is basically less than 1 over n, right. Now, this 1 over n, we can make it even smaller, okay, by multiplying things by a constant c or things like that. We can make this even smaller. Okay. So, instead of choosing a sample with probability 1 over epsilon n log n, we can multiply that, we can increase p slightly to make this even smaller. Why do you want to make this even smaller? because we want to now argue. So, this is for a specific subset, large subset, right. There can be many large subsets, right. There can be many large subsets. So, we want to add those failure probabilities. Okay. So, we want to multiply by that, and therefore, we want to make this even smaller, so that when we add all of them, the probability is still less than 1. Okay. So, all I am saying is that the probability that we miss even one among all the large subsets, okay, is less than or equal to 1 over n to the power. Now, I am writing 1 over n, but as I said, we can argue that we can make it even 1 over n to the power c by a corresponding c there. Okay, but let me not add the c. I am just, if I assume that the number of large subsets is not that large. Okay, so, it is basically going to be multiplied by number of large subsets. Right. So, certainly my probability of failure is no more than the sum of these probabilities. Okay. So, as long as I can ensure, so this quantity I want to ensure is less than 1. If I can ensure that this is less than 1, it means that there is a positive probability that some sample will hit all the large subsets. Are you with me? Right. So, if this is less than 1, then some sample of size, how much? Well, the probability, from the probability you can also get a size, right. Probability is 1 over epsilon n log n. So, you multiply that by n, that is your expected sample size, right. Some sample size of size n over log n over epsilon, sorry. So, there is some constant factor, let us say some, I am just adding that c, some c times log n over epsilon, okay, will hit all large subsets, implying there must be at least one such subset. So, this is an existential proof. Right.
Then you are saying that the probability of missing even one amongst all the large
Right. Is just for each of these large subsets, the probability is 1 over n. So, I just add up the probability for all these subsets. They may not be, they are not, they are correlated, but I can always add it up, right.
When you say even one means that even if one is missed.
Right. Even if one, the union of the events.
Oh, so you are adding.
Yeah. I am just using the sum to bound the union of the events, that is all. So, there must be at least one such subset that hits all the, sorry, one such sample that hits all large subsets. Right. So, this is an existential proof that there must be some, at least one subset of that, otherwise the probability cannot be strictly less than 1. There has to be something by which we can succeed to hit all the large subsets. Okay. So, that is an existential proof. So, the thing here to note is, so till now it is very elementary calculation. In fact, I can draw your attention to something that we did a while ago when we are discussing these things like randomized incremental construction, etc. I did not actually complete the proof in the class, but I actually alluded to this thing. I showed the slides, but I did not go through it. It was basically this kind of a proof, not exactly this proof, but it was this kind of a proof. When we are doing the trapezoidal maps, I said that I want to make sure that I choose a sample and the sample defines some trapezoids, and then the other segments that are going to hit those, the unsampled segments inside a trapezoid, I should be able to bound. it was a calculation basically of this form. Okay, you can go back and refer to the slides. So one such sample is it will hit all the it will hit all the large subsets. Okay, so it gives me this number of C log n over epsilon. Now maybe there may be even a smaller subset. Who knows? There could be even smaller subset by which we can manage to hit all of them. But it turns out that people have actually looked at this problem, and they have not been able to prove much better bounds. I mean, it's believed to be kind of tight, modulo the constant factor C. So you need so essentially we are looking at a figure, okay, where epsilon is a parameter to the problem, right? My large population is described in terms of epsilon, and even if epsilon is not a constant, I said it has to be a constant between 0 and 1. What do I mean by constant? It's some fraction basically 0 or 1. So all this calculation that I did doesn't depend on the fact that epsilon has to be 0.1. It can be much smaller than that. Anything that whatever epsilon is, this is parameterized on the basis of epsilon. So this subset that we are picking, okay, is a function of epsilon, and that's to be expected. The smaller the epsilon, the larger the sample has to be, right? Because if I want to hit smaller subsets, I need more and more sample. Right? But the thing that sort of kind of is the sore point, okay, is this thing. Okay? If it were not that, okay, then we should be happy. In fact, you can prove that it is completely tight. I can't do anything better than picking a sample of size about 1 over epsilon. That you can argue even with a linear, just look at the points on a line, and I want to hit every subset of size epsilon. I can't do with less than so many samples. Can't be done. Okay, so that's tight. But this log n is the only disturbing factor. Okay, so and that is what led to much of the development that we are going to talk about. Okay, so when can we essentially do away with the log n factor? Or in other words, when can I have a hitting set of size roughly about order of 1 over epsilon? Okay. So now this is the way we did the calculation didn't make any assumption about the subset system. It can be any kind of subsets, okay, except that we are hitting the large subsets. Now if we constrain the subset system to have some properties, then we can actually do away with this, okay, and that's what this theory is about. Okay. All right. So with that introduction, let me lead you into some definitions. Okay. So we'll essentially be exploring some subset systems, okay, with certain kind of properties where we can do this hitting set, and finally I'll not today, but sometime next week I'll end with a lecture where I'll show you that under what condition, especially in the context of subset system in the Euclidean space, okay, it most of them actually satisfy the property so that we can actually get a small hitting set. Okay, that's what the connection to geometry is.
If one element is part of some constant groups, constant subsets.
See, those are things that people will talk about when you're doing a linear programming formulation, etc. So this has got nothing to do with it. It's a purely combinatorial thing. You'll see. It's quite surprising. It's a very powerful thing. Okay? What you're saying is a sufficient condition. Okay, so for that I will define a notion of what is called a range space. Now range spaces has already been introduced in the context of range searching, right? Okay, so I'll kind of again recap those definitions. So range space, let us say S is a tuple x comma R, where x is a set of points, may be infinite, okay, and R is a family subsets X. Okay. Normally we will be talking about finite set of points. Okay. So, one way to specialize that is to talk about restriction. Okay. So, for okay, so just to give an example, okay, what I mean by this. So, my x could be set of points in the line, okay, and R could be closed intervals. So, that is the range space, okay, or this is one example, okay. X could be, let us say, set of points on the plane. So, these are clearly examples of infinite systems. Right. Okay, one way of restricting or making things finite is talking about restricted range spaces. Okay. So, if you say if y is a subset of x, okay, then the range space, okay, restricted to y, okay, is defined as y, okay, and the range is restricted to y, okay, and what is the range restricted to y? Okay. So, in particular, y can be finite. So, if y is a finite set of points, then everything is finite, right? Even the subset system, the family of subsets is also finite. Okay. This is an absolutely general and useless definition, right? I mean, what we are really looking at is a property of these range spaces, okay? And that property is the following. Say that a finite subset okay, shattered, okay. Let us say if the range space restricted to y, okay. So, the range is the number of the ranges restricted to y is the power set of y. Okay, quick example. Let us say example 1, points on a line and intervals. Right. Consider y is a set of 2 points. Okay. So, here is my line, my y is these 2 points. Okay. So, what is the size of the range is restricted to y? I could have an interval containing this, I can have an interval containing this, I can have an interval containing this, and I can have an interval not containing any of the points. Okay. So, number of the number of ranges restricted to y is the power set of y. Okay. Maybe I should actually use both sides. Okay. Okay, now let us see how about 3 points. Can this be shattered? Can we have all possible subsets where my subsets are defined by intervals? Okay, let us call them A, B, C, the 3 points.
No, because if we have a subset containing A and C.
A and C, we can't help also picking up B, right? Okay, so it can't be shattered. Okay. So not just these 3 points, but no 3 points can be shattered by that range space. Okay. So, so that's what we are looking at. So this is basically what leads us to the definition of the VC dimension. Okay. So the VC dimension of a range space is equal to XR is let us say delta if and only if for all y such that y finite y, okay, y is greater than delta y can be shattered and will I mean to complete the definition maybe one should write that if for a size and there exists, okay, and there exists a subset of size delta. Sorry, this cannot be shattered. So it is the largest cardinality subset that can be shattered. That is the VC dimension. So for the example that we just had, the VC dimension is 2. So some essentially comment some range spaces may have infinite VC dimension, or let us say delta equal to infinity. That is, it is not a bounded VC dimension. Can you think about an example? Okay, here is an example. So consider this range space S conf all points on the plane, okay, and the ranges are all convex subsets. So I take, let us say, so I'm and my I take an arbitrary set of points. Sorry, no, not an arbitrary. I take a set of points that are on the convex. So I have to argue that the VC dimension is at least n for any n, let us say. Okay. So I take all the points in convex position. Okay. The points of R square, the set that I am looking at, they are all in convex position. Okay. And my ranges are convex subsets. All right. And I claim that I can capture exactly any subset of this using convex subsets. Why? Because any subset of points in convex position are convex. I want these 3 I can get these 3, whatever I want. Right? So, this is one example of a range space with infinite things. Now, how do you actually go about proving finite VC dimensions? I mean, how do you prove? And I am giving you a subset system, sorry, a range space, and how do you actually argue what is the VC dimension? May or may not be easy, right? So, for example, just consider this one. So, here is a range space S prime, which is okay, suppose it's points on the plane, okay, and disks. Right. So, what I mean is that here points, okay, and my subsets have to be basically disks of any size, does not matter. Etc. What do you think is the VC dimension of this? Is it, let's try to argue, is it at least 2? Okay, at least 2. Is it at least 3?
3 points are on line.
So, see, as long as there is one subset that you can shatter, as long as there is one subset that you can shatter, it's good enough. Okay, you don't have to shatter every subset of size 3. So, if I take 3 points, I should be able to draw disks containing these, these or these. I should be able to find such sets of points. So, I claim that it is at least 3. Okay, and to say that it is no more than 3, then we have to somehow argue that if there are 4 points, there is no way that it can be shattered. So, here is a quick proof, okay, hand waving proof a little bit. So, the 4 points, okay, may not be in convex positions. So, one point could be inside the triangle. Can you shatter this? Can you shatter this? No way, right? Because if I want to have these 3 without excluding this, I can't do it. Okay. So, then no point is in the convex combination of the other 3 points. So, then if you take now these 4 points, okay, then you should be somehow able to argue the following, that I want to include these 2 points and not the other 2 points, okay. And in other cases I may want to include these 2 points, but not the other 2 points, okay. And if it were so, then I will have 4 intersections, which is not possible. Between there cannot be 4 intersections, okay. So, it is not possible. So, the VC dimension of this range space is 3, right? And things can become quite difficult, So, one very interesting VC dimension is points. Okay, so this is what you can try. If you don't succeed, we can talk about it next time. So, this range space, let us say S2, S double prime, points in the plane, okay, and half planes. Try that later. Anyway, so I should probably end today with just this remark, that it turns out that VC dimension is a very crucial property of many subset systems, and what we will eventually end up proving, or that is what our goal is to show that this is the result that we will basically prove, okay, over the course of the next 2 lectures, that a range space with finite VC dimension has So, this epsilon net is essentially the cover that I was talking about. I want to cover every subset with size at least epsilon times n. Okay. So, that is called the epsilon net. Okay. This is basically covering all subsets of size greater than or equal to epsilon times n. Okay. So, range specified has epsilon net of size that is only a function of epsilon. So, we do not have any log n factors with that. If my fraction is whatever 10%, then it is purely now that fraction is not 1 over epsilon. Okay. So, that would have been ideal. So, but it turned out to be closed not very far away from that, it will be some polynomial in 1 over epsilon. Okay. That is what we will end up proving. So, it will take some work, it will take me a couple of lectures through that.